Alright, so this semester we're starting with waves. If you remember, in 2210, we talked about simple harmonic motion, or oscillations. So if you have a spring, and you hang a mass from it, and you pull it down and let go, it'll bounce up and down. It'll oscillate. So some terminology that we used. We talked about amplitude. What was amplitude in terms of oscillatory motion?
The range?
It was the distance it moved, the object moved, and it was specifically measured from the equilibrium position. So if you just hung the mass from the spring and let it sit there stationary, that would be the equilibrium position. You pull it down, however far you pull it, would be the amplitude. The maximum distance from equilibrium. Now, in terms of oscillation, we used a capital A to represent it. In waves, we're still going to be talking about amplitude. Amplitude still has the same meaning, the maximum distance from equilibrium. But there's different types of waves, and there's different ways in which the materials can move. And so our book uses a capital D just to represent displacement in general, and then a subscript of max. So D max is the symbol we use to represent amplitude, but it has the same meaning. It's the maximum distance your material moves from its equilibrium position. Period. What was period?
Time it takes.
The amount of time it takes for what?
One oscillation.
To complete one oscillation. So if I pulled the mass down on the spring and let go, it would be the amount of time it takes to go from the bottom all the way up back to the bottom. Which is the same amount of time as it would take to go from the top to the bottom back to the top. Or from the middle back to the middle. The symbol we use is still the same, capital T. So period is the time to complete one oscillation. What about frequency?
How many times it takes per second, oscillation per second?
Right, so the number of oscillations it completes in 1 second. The symbol we use for frequency is a lowercase f. Remember frequency, regular old frequency was in hertz. Frequency is the number of oscillations it completes per second. Or what fraction of an oscillation it completes if it doesn't complete a whole one in 1 second. Question? What was angular frequency? Yeah.
Where the period is broken down into 360 degrees or 2 pi or whatever.
Exactly. So it's basically, instead of leaving it in terms of an oscillation, transferring it into radians. So breaking it into 2 pi radians.
Yeah, EE would do both, which is dumb.
The what? Sorry?
In all my electrical engineering classes, we switch back and forth.
Yeah.
Oh, that's good.
The symbol for angular frequency is omega, the Greek letter. It's simply taking frequency and putting it in terms of radians per second as opposed to oscillations per second. So, one oscillation is equivalent to, say, a full circle. A full circle has 2 pi radians. So all we need to do is multiply this number by 2 pi, and we now have units of radians per second. Okay. With waves. This here would be considered what we call a medium. A medium is a material that a wave can travel through. A wave is simply a disturbance of a medium. The medium itself doesn't physically go back and forth, but I can produce a wave by disturbing one of these rods. Okay? Each of these rods is connected together by a really thin metal strip down the center here. So the equilibrium position is this right here. The amplitude is the maximum distance any one of these bars, as we're falling apart. So the maximum distance any one of these bars moves up or down from that equilibrium position. Okay? Waves are very similar to simple harmonic motion. If you look at just one of these bars, it's going up and down, oscillating just like a mass on the end of a spring would. What makes it different from oscillations is that each of these bars is connected to each other. So if I make one of them oscillate, then they all end up oscillating. Now notice they're not all at the maximum peak at the same time. They're not all at the bottom at the same time. Some of them are going up while some of them are going down. They're at different positions at different points in time. Now the wave itself is the disturbance. So if I just flick this once, this is the wave. And it reflects back and comes back to the other end. Notice the medium itself, this bar didn't travel down and come back. But the disturbance that I created travels down and comes back. Waves are a disturbance, basically. It's something transferred from one particle to another, or in this case, one rod to another. There's two ways we can graph a wave. We could take a digital camera and just take a snapshot. So at one moment in time, take a snapshot. We would see something that looks like that. That's what the medium looks like as the wave's traveling through it. This axis would be a position axis. It would be telling us, we would be able to decide which rod we wanted to look at. So basically, you can think of this as the x-axis. Each of these rods has a different x position. If we just call this one 0 because it's the farthest one down, each of these they're about a centimeter apart. It's not totally consistent. This would be a snapshot. This would be one way to look at the graph. So this is at one moment in time. Looking at the whole medium. The other option would be to take, say, a video camera. Zoom in and focus on just one of the rods and look at what one of these rods is doing over time. Now the graph itself would look very similar, but this axis would no longer be x because we zoomed in and looked at just one rod. This axis would be time. Okay? So we were looking at what this one rod is doing as time goes on. This would be the video. So one piece of the medium. We can get different pieces of information from these graphs. In both cases, the axis represents the equilibrium position. So from equilibrium position, either up or down, is our amplitude. And that is the case either way. And I'm sorry I didn't draw these exactly perfect. It should go up the same height it goes down. So we can get amplitude off the graph. This graph is the one that's comparable to what we were looking at when we talked about oscillations. We looked at what, say, the mass on the end of the spring was doing as time went on. Anyone remember what that represented? Period. And of course, if we go valley to valley, it's also period. We go from any one point to the exact same point, it's period. And that's still the case for our wave. If we are graphing one piece of the medium, so if we're videotaping it basically, if we're graphing what one piece of the medium is doing over time, that peak to peak, valley to valley, that is the period. There's a certain amount of time from one peak to the next. This one's a little different though. This is the snapshot. This is the picture at one instant in time. This axis isn't time. This has a very specific meaning though.
It's wavelength.
Yes. Not period, but it's called wavelength. The symbol we use for wavelength is the Greek letter lambda, lowercase lambda. Wavelength is something characteristic of a wave. All waves have a specific wavelength associated with them. Okay? So wavelength is simply the distance, the actual physical distance from one peak to the next. Okay? Now this one interesting thing happens. The speed of the wave, how fast it actually travels, depends upon the medium itself. So regardless of how fast I shake these rods back and forth or up and down, the wave itself still travels at a set speed because I can't change anything about this medium. What I can change is how fast I shake it. How fast I'm moving this up and down is the frequency. I'm creating a certain number of oscillations per second. You all right with that? If I change the frequency, we are getting some interference, yes. I'm going to have to show you on the slinky. It turns out, though, if I change the frequency, that will automatically change the wavelength. And we'll see that correlation. The slinky works better. So we'll do that here in a second. At any rate, with waves, we have an equation that can, we need an equation actually, that can describe not only what each piece of the medium is doing at one moment in time, but also what one piece of the medium is doing over time. So our equation, the displacement of the medium, our function is going to depend upon x, which piece of the medium we're interested in, and t, what time we're interested in. So we have an equation that's going to have two variables in it. Position, just meaning where in the medium, and time, what time are we looking at it. It looks very similar to the oscillations in that it's going to be a sine or cosine function. But we have to incorporate both x and t. So we have the amplitude out front, so d max remembers amplitude. Generically, your book writes it as a sine function. What's the difference between a sine and a cosine function? 90 degrees, the starting point, basically. Your book just writes it generically as sine. You can write it as cosine. The equation looks like this. K is called the wave number. It's related to the wavelength. It is equal to 2 pi over wavelength. So its units, well, the 2 pi is radians. Wavelength's an actual physical distance measured with a ruler. So it's the distance in meters. So the units of K are radians per meter. Omega, we already know. Omega is angular frequency, so it's 2 pi f. It has units of radians per second. Phi naught is the phase shift, or phase constant. That just makes sure your function satisfies the initial conditions. That makes sure the starting point of your graph matches what this function would graph. You can figure out what the phase shift is if you know the displacement of any piece of the medium. So if you know where, say, this end of the rod here is at time equals 0, if you know how far it is from equilibrium, you can put in how far it is from equilibrium. You know the end is x equals 0, time is 0, you can solve for that constant. Okay? This whole term is called just the phase itself. Not the phase shift, not the phase constant, just the phase. Your book uses a phi without a subscript to designate that. We'll talk more about that a little bit later. So this is the form, the generic form for a wave, to describe the wave. X is wherever in the medium you're looking at, T is what time you're interested in looking at. We have some familiar concepts: amplitude, period, frequency, angular frequency. We've already talked about those in 2210. That should be familiar. The new piece that we have is this wavelength. So the wavelength is the physical, actual distance in meters from peak to peak or valley to valley, from any one point to the identical point. Questions so far? Yes, please.
So like, I guess you could use that to model any position on the intermedium. So like you could say 2 inches from the origin, you just plug that into X.
Exactly.
And that T, and as you pump values into T, that'll model that single piece.
Exactly. Exactly
Okay.
right. Yeah, so whatever piece of the medium you're interested in, plug in its position, and then you can see where it is at any point in time. What if we took the derivative of it? This is a function of displacement. What do you get if you take the derivative with respect to time? Velocity. If we took the derivative with respect to time, that means you just treat x as a constant. T is your only variable. You would have an equation for the velocity of that piece of the medium at any point in time. And you could plug in the x value you're interested in, the time value, and you'd know how fast it was moving. And take another derivative and get acceleration if you wanted. Please keep in mind, though, if we take the derivative of this function, that gives us the velocity of that piece that's moving. That does not give us the velocity of the wave itself. It doesn't tell us how fast the wave will move down here. It only tells us how fast these guys are moving up and down. Okay? It's an important distinction.